Hello, everyone. So let's give a little bit of time for people to join. I would like to do a quick sound check before we start. If you can hear me, please type yes in the Zoom chat tab. Okay, great. Thank you. Let's give a few more seconds. Okay, so hi and hello, everyone. I would like to thank you for joining us today to hear from Ashrith Barthur, who will talk about the benefits of using AI and ML to prevent and detect fraud more efficiently in the finance industry. My name is Bruna Smith, and I'm on the marketing team here at H2O.ai. And I'd love to start off by introducing our speaker. Ashrith is the principal security scientist at H2O.ai. What this means is that he gets access to some really interesting data sets in malicious behavior around the work in the field of network security, electronic fraud, and crimes. He finds malicious behavior fascinating to study as new techniques are coming up every day. So before I hand it over to Ashrith, I'd like to share that we'll have some minutes for Q&A at the end of his presentation. So please feel free to send us your questions throughout the session via the Q&A tab on Zoom. So without further ado, I'd now like to hand it over to Ashrith. Welcome, Ashrith.
Thanks, Bruna. Good morning, everyone. Thanks for joining in. I hope you find the talk useful. So today's talk is primarily going to be about how to detect and prevent fraud, across financial institutions and things that use financial instruments. So just a basic quick run, Bruna has basically given a good introduction of mine. So that's essentially, hang on, let me just make sure. That's essentially who I am. So I probably don't need to go there. If anybody has any other questions about, what are the other things that I do out at H2O, please let me know, and I'd be happy to answer that. So today's talk essentially covers, let's say a series in which we are doing different kinds of, analysis, different kinds of motivational speaks about fraud itself. And today's coverage is much more about use cases. How do we work with different fraud use cases? What are the kind of applications that we develop? What are the kind of models that we develop? What are the approaches that we take? How does detecting fraud and actually preventing it look like from end to end? So in general, these are the things that we are going to cover. Basics. Well, what does fraud look like? How is it? What is the status of it currently in the industry? The areas of focus. This kind of brings about into focus what I'd given in a previous talk. The reference for people who are uninitiated about the previous talk, don't worry about it. We'll actually send out a link and everything for the previous webinar. It's in this talk, I'll be having something really concise so that you can always use the same information and build up how you work with fraud and detecting fraud for that matter. We'll also talk about some use cases, specifically two specific use cases that we have, where we've done really well in terms of fraud, is how I would say. How does it actually how does all of this actually come through? Like what do you need from an end-to-end perspective about how fraud needs to be handled, how the systems need to be designed, and so on is something that I'll go through. I would say I'll quite briefly because I think it's, for me, it's I feel it's very important once you develop the, figure out the data set, build the features, set up the model, find a way of consuming the whole system. It's actually a very important thing to see that you're actually out there solving what you set out to solve. And so all of this coming together is a good way of identifying that you solve the problem, and especially fraud in this case. And then we'll go over conclusions and discussions. So what are we looking at when it comes to fraud? What is the current status of fraud itself? So there are so much of the fraud space is covered by rules-based systems, and it's not something that requires a lot of brain power to actually identify. Why so? Primarily because rule-based systems are extremely fast. They're really good in identifying behavior, and they're extremely fast. Essentially, speed is the one thing that actually matters when it comes to rule-based systems. But there are some limitations when it comes to rule-based systems as well. The features are very limited, and that's something that you pay as a part of the price for the speed. The feature space itself is limited. When I say feature space, it could be transactional, it could be geographic, it could be different indicators that are actually much more in the same range. But but someone might come and ask, what, I don't need the speed, but why is it that you insist that fraud needs to be detected so quickly? If you look at fraud, one of the things is always loss minimization, and that is one of the reasons why speed is always an important aspect of fraud minimization, and which is one of the reasons why most of these systems are actually rule based, and that's actually one of the reasons why they're actually very popular as well. But do these rule-based systems actually end up solving the problem is a big question that we almost always have. I would largely say yes, because we have been, pretty successful in solving fraud. But I would kind of be much more inclined now to say, it's losing its grip, primarily because of the way things are scaling. One of the things is that the current rule-based system have a lot more trust in it than actually giving something decisive. The detection of anomalies are kind of interesting, to say the least. Then there requires some amount of post-priming. Essentially, you need to see a behavior enough number of times to actually be able to identify it as something that's unique. So for example, if you have like burst transactions, it takes some amount of time for burst transactions to be actually captured and then identified as fraudulent. So these are some of the limitations that tend to have with rule-based systems, not just some of the basic problems that you have with rule-based systems. So fraud as it stands right now has three parameters that defines how the fraud systems work. One, of course, is the speed. The other one is the model type, and then the feature in the feature space. So you kind of have to manage between these three, and that is very essential for you to actually design your fraud model, design how it's consumed. Actually, for that matter, the very speed itself defines how the consumption actually happens. If your models are not fast enough, if your data set is not ready enough, then your consumption might actually be very low, which means that the usefulness of the model might actually be little. So when you look at this, there are three aspects of the fraud itself. Three aspects that define what it is: speed, model type, and the feature space that actually look at. Now, how does it how different is it when it comes to rule-based and when it comes to, let's say, AI or model-based for that matter? In rule-based, your speed tends to be really high, because all you're identifying anomalies based off variations in rules that you've actually set up. The feature space tends to be very limited. The feature and the feature space, both of them tends to be very limited. In the AI or in the ML learning space, the advantage that you have is you can build many different kinds of models, starting from like GLM to GBMs to random forests, deep learning. Any of these models can be very extensively built. Your feature space is pretty large. You can go kind of crazy about the amount of features that you want to include to try and identify the fraud that you have. But the cost that you actually pay is the speed at which your response comes back. Simple examples are like, if you have like longitudinal features in your fraud detection, then your speed, then you kind of compromise on your speed, which is essentially a problem. So these are the fundamental two ways in which you can actually separate the fraud space. There is one more, which is kind of the third one, which is much more trust-based. A lot of systems actually use this where they outsource the modeling itself to another agency, providing with minimal amount of data. And this you can see with card processors, with some financial institutions as well. If you're merely looking at credit card fraud, if you're looking at, like, let's say purchase fraud or online fraud, then this could be outsourced to different companies as well, where some of them are trying to identify the some of them are trying to identify the validity of the user. Some of them are trying to identify whether the cards, the monetary instrument that's being used is valuable or not, and so on. So an amalgamation of all of those things is something that will come by. So trust base is another approach that companies actually use fraud detection as well. So we keep talking about why it needs to be fast, but I think one of the important things is what are we kind of looking at when you look at fraud models intuitively, or when you look at the whole space of fraud detection itself. What we would actually like is to have speed that is very similar to rule-based systems. And when I say rule-based systems, one of the reasons why we do say that is rule-based systems tend to have almost line speed. Line speed is the rate at which you can process transactions, process requests, or process sections, anything that you want to classify in this case. But then you also want to have a large comprehensive feature space, that comes out of like machine learning models. So essentially you want a combination of these two. But as we went through, in just a few slides in the past, there is a price to pay between the speed, between the kind of models, and between the feature space. So it's kind of a tightrope walk. You can get to the other side, if that's a term I can actually use out here, by getting out much more efficient models, but faster models and comprehensive models. So that's something that is doable, and that is essentially what I'll be illustrating through the use cases that we have in this session, that we kind of described in this session. So why do we need faster detection? I mean, rule-based systems are doing a fantastic job. I myself say that, they're pretty good, we're pretty successful. But what is the need to have much more comprehensive systems and much faster systems? I think we probably would have seen all of the reasons that I've listed in a much more linear fashion over a few years. I think because of a lot of changes that have happened around the world in the past year, all of these things have accelerated. Of course, I'm very strongly mentioning to much more online sales and much more acceleration of online sales because of COVID. So some of the problems that we do face is currently the rule-based systems have a really high error rate. There are about, some of the systems actually end about with 90% false positives, which essentially means that you are cleaning, for every 100 transactions, you're cleaning out 90 transactions, which could be false positives, for identifying 10 transactions. That kind of puts you in a bad spot, which means that a lot of effort is going in to try and identify your false positives within your transactions. That essentially needs to be reduced. You also have to match like the credit card line speed. So there is a top limit where it says there is 25,000 transactions per second, which essentially means that these systems can actually process 25,000 transactions per second, provided they can verify that it's actually fraud or not fraud, and so on. So you kind of have to scale that up as well if you can, which is very important. Online purchases are, of course, on the rise. And I had said earlier, COVID's made this a very big problem. Traditional approaches of purchases online have kind of become limited. There are much more electronic means of purchases. It could be electronic cards, virtual cards, and many different kind of instruments that you actually use for purchase. And there have been numerous reports. I think what we've observed is that multiple traffic purchases look very similar to Black Friday sales, which is kind of very interesting. And fraud generally tends to increase close to about 20+%, 20+% over year. So that's kind of really valuable. So there are some different kinds of frauds that I'll list out that can use this kind of an approach, which will kind of set the context of the kind of fraud that we are looking at. So some of the things that we can look at is online purchasing fraud. We can look at phishing fraud, identity theft as as one of the fraud means, credit card, of course, and social media fraud. So these are some of the kinds that we have worked in the past. We have successfully implemented solutions in the past. It's not. This is not a limited set. I mean, there are many different forms of fraud. There's pure transaction fraud as well. And these are some things that actually um, something that have a huge loss value. So this is something that we've considered as well in evaluating it here. And when we look at the areas of focus that we actually have, there are essentially three areas of focus. And for the people who have not necessarily seen the previous stuff, it's totally fine. I'll send you the link. Bruna will help me out, send me out the link. There was a certain aspect of what are the areas of focus that we need to focus for fraud is what we discussed. And these are very simple things. These are feature engineering, model, and business decisions that actually make sense for trying and building out much optimized fraud models. So in terms of the feature engineering, so essentially, you build really strong models. You build really strong features. Try and make as much zero prior knowledge as possible. So the idea here is that if you have features that are much more dependent on historical data set, then your models tend to become slower. If you can try and get features that don't necessarily need a lot of historical data, then it is actually much more valuable in terms of speed, in terms of how big the feature is, and so on. You can keep your longitudinal features to the minimum instead of looking at, like, let's say 3 months, 6 months, 10 months, a year of transactions. See if you can actually make sense between 15 days to 30 days of transaction history. If you don't need to have features that constantly need to be calculated, just have them calculated and set it up in a database, which you can quickly call and use them. Use light data structures. I mean, you don't necessarily have to use integers. You can use like booleans if you just have like a binary state in certain features. So these are some of the interesting things that come up in features. And in modeling, you can keep simple models. GLM, if it works perfectly, that's great. You don't have to like make a super deep model. Have many models. I think this is something that is kind of being put out as information much more frequently now. Models have become commoditized. It's not a price position anymore. You put out as many models as you can, to make things as valuable as you can, and keep things as parallel as you can. So, have as many models as you can to make decisions. Use different models for different subsets. If you have data sets that vary a lot, then use different models for these different subsets. Use different models for feature sets as well. If you have different feature sets, then you can use different models, but you can also keep the model, not very deep, pretty light, and so on, and that actually is pretty useful for you. In terms of the decision, in terms of the business, look at how you decide based upon risk. Choose a good combination between your speed, accuracy, not just speed, not just accuracy, because I think the reasons we mentioned, scaling is a need right now, and you also need to be accurate. Otherwise, you would be held back by reviewing false positives all the time. Choose low risk levels, which actually would be much more valuable, where models are more accurate, and higher risk levels where they're less accurate. So you can actually compromise on that. So anomalies, try handling them separately. One model fits all is not a good equation. Anomalies can be handled as a separate model as well. You can segment the data set and then handle anomalies as well, which kind of makes it easy. So having generally set up the approaches that you use for fraud detection, What I'm going to do now is that I'm going to quickly jump into the use cases, okay? And some of these use cases might ring a bell for you because these are something that you might have worked on, or that's something that you're working on. This might give you an idea about how you could approach the same problem, and let's go from there. So the first one we're looking at is credit card fraud. So what we actually saw in the situation was the financial institution was processing a large number of transactions. Fundamentally, credit card transactions was something that they were concerned about. A significant percentage of these transactions were classified as fraud, which kind of comes back to the topic of discussion, that if, or rather one of the subpoints in the discussion, that if you have a lot of false positives to clear, then your efficiency is low, which essentially means that the amount of time you're spending on all of these transactions is actually very much higher. So you kind of have to reduce that. And there was a good percentage of all of these transactions which were actually false positives. So they essentially needed to clear that. So what they wanted to do, they wanted to keep their transaction processing speed very similar to what they have, or they wanted to improve it. They wanted to reduce the number of false positives that they'd actually got. And they wanted to see if they can add much more signals to the models that actually existed. So these were the three fundamental needs. Everything else that we could add above and beyond this was let's say icing on the cake. So that kind of made it valuable for them. So one of the first things that we did is we actually looked at their data. So when we looked at their data, we saw that there was a very interesting skew when it came to the transaction amounts. We used this here, by the way, just for illustration purposes. I've split the space into two models, but in reality, we actually had many more models splitting across this space. So what we did is we actually split the space into multiple transaction amounts. And what we did is we used different sets of features for each of these segments. And we also used different models independently that were run parallel. So that essentially actually gave us much more value. So what happened was, as the transaction was widely distributed, we had a comprehensive set of features that we actually added to this to basically try and identify credit card fraud. But the problem that we ended up with was that with so many features, we didn't necessarily get the speed that we wanted. So one of the things that we could do was actually divide the space into multiple models, and then we also pulled out the outliers as a separate anomaly detection model in this case. The longitudinal features were actually very much limited, which meant that we didn't have to look back a lot into the history. So this kind of gave us an advantage about having models run in parallel, but still maintain the speed. So how did the results look like? Like what actually came about after we built the model? We did the whole feature engineering of the space. So the feature engineering space was significantly large, which essentially meant that there was a lot of information that we were looking at to try and identify if a transaction was actually fraudulent or not. By parallelizing the models and by actually adding much more comprehensive features, we were actually able to increase the speed to about 1.3 times the transaction rate that they were actually looking at. And this essentially gave us enough space if we wanted to increase the features as well. So we were already hitting 1.3 times, so 130% the line speed that they wanted. So which essentially meant that we could add more features if we wanted to match it to the current transaction rate. As we had broken down, as we had segmented based off the transaction amounts, we saw a wide reduction in terms of like somewhere between 35% to about 61% in different transaction segments. And the reason why these numbers tend to vary is because while in some segments, the confidence level is much higher in trying and identifying if something is a fraud. In certain segments, the confidence level need not be the same. So essentially, in those segments, the numbers could be much lower than compared to the segments in which the numbers are very much higher. So So this is like a use case where we did, manage the credit card fraud process, which essentially put us in a spot where we could try and like identify, we could try and identify different segments in the transactions itself. Using these segments, we built up feature sets. Much of the feature sets was actually homogeneous, but there was a good amount of features that were very unique to each of these segments. Then we segregated the space by having outliers purely by anomaly detection models, which essentially meant that we had parallelized it to another model, and each segment had its own model that essentially gave us the ability to kind of process all of this data at the same given time and still be able to match speed and not necessarily lose out on it. So having done that, let me switch to the next use case. So the next use case actually happens to be an online purchase and identity fraud. This is a bit more complex fraud problem than merely the credit card problem that we actually had faced. Here, the online retailer kind of had two issues. One was they were looking at identity fraud. A good amount of them, like impersonation was kind of in the data set. And they had fraud purchases, or in this matter, fraudulent transactions that was actually happening. They had some limitations. Essentially, they were dependent on the credit card transactions for trying and identifying, if the transaction itself was fraud. And then they had an external system which was trying and helping them whether a user was actually fraudulent, or whether the user was all right for them to process and go through and so on. So this was a slightly different problem. The speed was not necessarily the same speed that we had to achieve when it came to credit cards, but speed was still an important issue in this case. And I'll kind of explain, what their needs were. Maybe that will kind of give us an idea. So the problem was, much of the problem actually existed in delayed identification. I think this is the problem that comes up when you have something called as post priming, where you need to see enough of a certain behavior for your model to actually pick up that this is a fraudulent behavior. So this is some kind of a problem that they had. So any kind of like a shock fraud where someone comes in with, like, let's say, a fake credit card or a fake account or any of those things, and quickly scales up purchases, like $2, $5, $10, $1,000, and so on, and closes it immediately, was one of the problem sets that these guys actually had. Identifying this kind of behavior was actually a big problem for them. Their existing systems, either through the credit card or through the external support, did not necessarily help them out. So what it also meant was, shock was one of the approaches, but even if there were feeble signals, their systems did not necessarily capture it, which was a problem as well. The amount of fraud in the system was not large, but it was significant enough for them to actually say, that they are not able to take the amount of risk that the current level of fraud actually has. The other big problem, I think this is something that every online retailer or every online processor kind of faces, is that there is a loss of customer trust when you go through so much of an issue. The customer does not. If you randomly throw challenges, like, let's say, at the customer is not very happy that you're expecting the customer to solve a problem. For example, I think many of us face this problem when we miss a username and password, maybe like once. You have to do the reCAPTCHA multiple times, and it doesn't necessarily let you log in right after the first time you solve the problem. It kind of repeats itself about 3 or 4 times, and then it asks you to solve then it actually allows you in. I think this is something that they faced in a very big way, but they kind of did not have any other solution and I don't think they even had a two-factor as a part of the whole solution to try and identify whether this actually makes sense for them. Um, so they kind of had the customer trust was a big problem for them. So the way we looked at this was slightly different. What we did here was we looked at how the data looked between fraud and non-fraud data. So we were trying to see, what differentiates between these two areas. And this is something that I also want to remind, to the listeners or to the audience, is that the separation of space that we actually have could be by any means. However you seem you can divide your data is perfectly fine. I mean, you don't necessarily have to look at it by transactions, have to look at it by fraud and non-fraud. You could even look at it by segments, destination, like whatever feature set actually makes sense, whatever feature set that you can actually use to kind of partition the data space is great, for you to identify this. So in this case, we actually tried to separate the space between fraud and non-fraud to try and study, what are the different behaviors that we actually see. So from this, we kind of saw that products that were products that were essentially like needs, for example, like groceries, and like daily your essentials, like let's say soaps and shampoos and these kind of things, were less likely to be a part of the fraud purchase. You would happen to have much more interesting purchases with, like, let's say, televisions, fancy stereo systems, and so on. If you're going online and purchasing these things. So this was this is kind of a defining idea that we kind of took forward. We looked at this data across the entire organization, and we saw this kind of reflected that information. So we had different models for these different segments of data, which essentially helped us, try and identify when fraud might be happening in like a non-essential product, and fraud might be happening in like an essential product. So that kind of actually made a huge difference for us. The other thing that we also looked for is something called as secondary signals. I think some of you might have used this, some of you might have actually been familiarized with it. So a transaction is not necessarily the information that you get from your credit card, the information that you get merely from any agency that's actually processing identity information and so on. If you are an online retailer, you yourself actually have access to this kind of information. You could use your browser information. You could use the session information that's actually happening from the system. Like, let's say, number of purchases in the last 24 hours. Is there a change of IP address for that matter? And repeated purchases, are there any unique purchases, any extremely high value purchases, and so on. So these are some of the features that we actually added up into the data set, where we used this information to try and identify and try and differentiate rather between something that was fraudulent and something that was not. And it kind of gave us a lot of value in when we were trying to separate the space. So what did we actually go about doing? So there was already two sources of information that there was. One was the card classification, the other one was the identity authentication. So we added the third one, which was basically the online retailer secondary signals. So we added this information to the entire data set to try and make the data set much more comprehensive. The model was also divided. So we separated the model. Of course, everything runs in parallel, so that's kind of an advantage for different product segments, which kind of brought down the fraud space itself. We hardly saw any fraudulent transactions with essentials, while we saw a lot with non-essentials. So we had two models that came from the secondary signal. One was purely from the business section, which was more about the transaction, about transactions for that matter. The second one was about like system information. Where was this person coming from? What is the kind of browser that this person was using for that matter? is there any kind of a lock on previous purchases from this machine? Is there any information that we can get, and so on. Again, even in this case, we kind of moved the anomaly detection out because, as I've spoken about this, trying and identifying an outlier, across a data set kind of overburdens the model that is looking for this behavior. And these anomalies were actually looking at frequency, segments, and transactional values. The advantage of separating out the anomaly model was that we could actually have much lower thresholds to try and detect any shock fraud or any burst fraud, for that matter. And this was actually reviewed by fraud experts to try and tell us whether this is actually a valuable feedback or not. So some of the results. So we significantly increased in the features, which kind of improved the inputs for the model. So we did see, so there were lots of relative features, lots of longitudinal features. Of course, we kept that space to the minimum as well, which helped us kind of go through different surges. If you had like Black Friday, Cyber Monday, any of these things, you wouldn't have a problem where the model would understand how to scale up and scale down, which is, or in this case, I wouldn't want to say model, let's be a bit specific. The features would know how to scale up and scale down. The secondary signal definitely improved our fraud detection. The whole response was much more real time. Almost real time. And now the online retailer was actually able to provide feedback to the card processing system, so which kind of added much more value to what the online retailer was actually generating. The random security challenges actually reduced by about 70%, which was super valuable in terms of like reducing customer complaints. The security challenge became much more accurate. 90% of the times when there was fraud, we were able to try and send random security challenges, and that kind of dissuaded people from not getting in. So which kind of added value. Things became, of course, faster. Secondary signal was available at source, which means that decisions were much more faster for us to identify. The models were very parallel, which means that we never compromised on speed. The segregation of space helps. So it's like segregation, and then parallelizing the model kind of helps the whole process. False positive reduction was really high. The anomaly models were, of course, really successful for us in this case, because they were able to identify all kinds of behavior, even subtle behavior. The advantage of that was they were also able to scale when it came to increase in volumes or increase in transaction levels. So having spoken about these two use cases, I briefly want to take some time, before we start. We have some question and answers. How does all of this, kind of come together? Essentially, when you're looking at any data science problem, forget it for a moment that this is actually specifically about fraud. We'll definitely get back into it. When you're looking at any data science problem itself, you're looking at, the raw data, processing of the data into something that is actually useful as inputs. Then you're looking at, creating a model scoring. And then you're looking at how do you consume this information? The consumption of this information has to be, you either have automated systems that make decisions for you or in lieu for you, and then, they take care of the whole thing. Or you have people who are sitting and evaluating outcomes of these models and are like the gatekeepers of what decision actually gets back into the business. So there are two different ways in which you have to do this approach. You can do this approach rather. But this entire pipeline is something that is very, very important to follow. If you just do the feature engineering, you're modestly using your data science team, your AI team, or whatever you would like to call your advanced analytics team, for that matter. If you're using the model scoring and then just creating some features and then using model scoring, you're essentially doing the same thing, but maybe a bit more improved outcome. But if you do the whole thing end to end, then you're maximizing your machine learning, your data science team, and all the all the resources that you have to do advanced analytics. And that kind of actually is very valuable. At least in this case, how do we do it? We have like driverless AI and H2O that actually, creates the features, and builds the models. Then we deploy the model as well, and then we have Wave, which is a new framework where visualization of the outcome is kind of really valuable as well. Of course, this is an example of how the entire pipeline sits, but many of you might have many different approaches of how this pipeline actually needs to sit in your organization. So that's of course something that I would defer to you. This is just an example of how we do it, when we are involved. But right from features to model scoring to consumption of the outcome of the model is very important for you to see the entire the entire life cycle in this case. And one of the reasons this is actually a lot more useful in fraud is because you could create features but not necessarily process it. Then it holds very little value. You could actually score the data set, right? I mean, you could create features and score the data set, which essentially means that there is nobody who is consuming what the models have actually decided, which again, you're not using the entire scope that's available to you. But if you actually use it, if you actually use the outcome of fraud, you can actually, build up much more value for the organization that you're working in, or for the kind of work that you do when it comes to detecting and preventing fraud in this case. Just a quick reminder about why fraud detection still needs to be fast. As I was saying, we have a really high error rate when it comes to the existing rule-based models. Credit card processing tends to have a limit. With online purchases, these numbers are only going to increase, which essentially means that we have to scale up. I mean, fraud detection actually has to scale up. Fraud is increasing at a really high rate. And this is pre-COVID, by the way. This is not even, post-COVID. So which essentially means that this 23% might not be a real number anymore. It might be much higher than this. So, these are the essential reasons. These are the reasons, for that matter, why it's important for us to scale up fraud. And this could be any of the kinds of fraud that we just we listed out or we spoke about in these two examples. In terms of the conclusions, I would just like to say, efficiency has to be across all of these levels. It could be, across your approach, let's say data science, your engineering itself, model engineering itself, or your business when it comes to like the kind of risk that you take and so on. It could also be in the tasks, purely in the feature engineering part or in the modeling part. I hope these use cases kind of give you an idea of the kind of modifications that you can do in your pipeline or in your task, where it will give you a lot more value for what you're doing in terms of detecting fraud. Having said that, there are some points of discussion that I kind of thought could jog and could help you out think of some problems that you actually have. And I think we are kind of open to questions. We have about, I think, 18 minutes or so. If there are any questions, happy to take them.
Yes, we have a few questions in the Q&A tab. Do you want me?
Oh, sure, Brahma. Yeah, please go ahead.
Yeah, I can help you. So doesn't rule-based systems require intense computations during every execution in runtime?
Okay, so that's a really good question. And the reason is because a lot of rule-based systems have been very well optimized for line processing. So essentially, they don't require so much of computation, and because rule-based systems are not as deep as the other models are, they are very quick. And then that's short answer is they don't require as much computation as, like, let's say, other kinds of models might require. But I think
great.
We've I just do want to mention that I think computation is used to be very important, but it's not so much anymore. If that's one of the reasons to consider.
Great. There's another question here. How would you measure, quantify success of fraud detection models? Precision/recall tend to not completely paint the complete picture. If a model is so successful that it completely stops certain segments of fraudsters, then our recall and precision tend to go down on the remaining fraud. So it's a really long question, but I think that's the bulk of it. So how do we measure and quantify the success of the fraud detection models?
I think I think that's a very fair question, and I would actually, let me look at the person. I'm guessing that's
Nick.
Nick. Okay.
Yeah.
So Nick, I think that's a very fair question, and the reason why I think what you say is probably rings bell, and yeah, I mean, is very valuable for a lot of people across the audiences, because we tend to use one model across many different spaces, which essentially means that our data is naturally heterogeneous, and you can reduce that a lot. You can segment that in multiple ways. You can break the data apart in multiple ways, parallelize these models, and actually make use of the fact that models are much more easier to churn, to try and bring about much more value in terms of each of these individual models. And then you would kind of see, your precision, your ability to actually classify fraud, in a much better way. Let me try and I'm actually unable to read because of the screen, but yeah, go ahead, Bruna. Please.
I can send it over to you if you think it's easier.
Yeah, I can. I mean, this is probably a longer question, so I wouldn't mind if you would like to shoot up an email to us and we can reply to you.
Right. Okay. Eden is asking, why different models after segmentation instead of adding the segmentation, such as a product, as a feature to a model like random forest?
Fair enough. I think I kind of briefly added this, briefly spoke about this in the previous, while I was answering the previous question. So the idea is we want to try and parallelize the space as much as possible, but not lose out on the heterogeneity of the data as much as possible. So it's kind of, it's you moving from speed to feature space to model type as an area of compromise to, how heterogeneous do I want my data? How homogeneous do I want my data, and how much of variation do I see in my data? So you're kind of changing the problem to something else, which is much more fundamental as a data scientist for us to try and understand. So, which is why segmenting it and creating it in a larger, like segmenting and then building models independently for each of these segments is actually valuable. But if you don't necessarily have that much amount of data where you need independent parallel processing for, like, let's say, each of these segments. Let me give you an example for the product segments that we were talking about, right, where we divided the data set. They were processing, I think, close to about 8,000 transactions per second. This was the essentials. I think in terms of the non-essentials, they were probably processing about 2,000 transactions per second. And this is kind of a large volume for them when they were trying to make like a fraud or a non-fraud decision. And which is why segmentation actually made sense. But if you're doing about 100, 200, 500 transactions per second, you're absolutely right. Segmentation could merely be a feature in the model itself rather than actually having a separate model altogether.
Great. Eden is asking, how do you make sure that using multiple models is still interpretable?
So I think that's a very fair question. One of the things that you do run into is this space where now, because you have a different set of features, different model approaches, the explainability of each of these models tend to slightly vary from each other, and that's still okay. because you're relying on each of these independent models for, let's say, each of these segments, the explainability, or in this case, if you're looking at Shapley, or if you're merely looking at like a surrogate model to try and explain, how the data set is, that's still okay. But just use it with the same set of features that you use the initial model with, just like good hygiene in terms of data science, and that should still be fine.
Okay. Paul is asking, what systems are usually in the production environments? For example, Flink, Kafka, yeah, etc.
Yeah, in terms of so you have to understand when transactions are coming in, they're using a whole different approach for transactions to actually come in. But because fraud detection systems are much more down in the pipeline, they tend to have queuing systems. So in this case, they could be using like any MQs for that matter, or they could be using even Kafkas for that matter, if it's okay for some things to wait. So what we've largely seen different kinds of MQs. Kafka has been there. Flink, not so much, but we do have seen it. But if you purely numbers, I think we've seen Kafka more than Flink.
Okay, Michael is asking, anything on healthcare billing fraud?
So I don't necessarily talk about the topic. There's a colleague of ours, I think Bruno, we can probably provide that information as well, she's very well versed in it. I think if there's an upcoming talk, we'll definitely email that out to you.
Yes, okay. Yeah. Great. Eric is asking, how is imbalanced data managed?
So one of the things that we do suggest is if your transactions have a state, meaning you're looking at accounts historically, these accounts have been fraudulent or non-fraudulent, and then suddenly something has become fraudulent. If there is some form of state, then it is much better to use a weighted approach in terms of fraud than to use oversampling. I strongly recommend oversampling as an approach only when you do not have state to maintain across an account, across purchases. For example, oversampling is a perfectly fine fraudulent method when you're looking at guest purchases, when you don't want to sign into a website, and then you're looking at all the kinds of signals, and then you find that something is fraud, something is not. There is no state. You don't know essentially who the guest is, but you can of course gather some information. So that's you can do oversampling in that approaches. But if you have state, it's always better to use weights in an imbalanced data set.
Sorry, I was on mute.
No, that's fine, Bruna. Yeah.
So do these businesses manually review all of the fraudulent transaction users detected by the model before taking any actions due to the prevalences of false positives?
Sorry, Bruna, let me just read.
Just click on the Q. Yeah, click on the Q&A tab, and you'll see.
Do these businesses manually review all of the fraudulent transactions users detected by the model before taking any action due to the prevalence of false positives? I think Candace, that's a really fair question. No, they don't. Transactions that are identified as fraudulent with a really high probability are not reviewed individually. There is something called as a bulk review process where, or you can sample and you can review. But things that actually have low prediction values in terms of, fraud are actually reviewed manually, or transactions that have actually been tagged as anomalies are reviewed manually individually. Let me jump to, so what kind of unsupervised machine learning model types would be the most appropriate for the fraud detection and credit card? Okay. I would say one of the best things to do is something called as probability clusters. So you can build clusters with your data set and see what's the probability of your clusters actually forming fraud or non-fraud. which I've seen amazing success with. It's super valuable if that's an approach that you want to take. One of the new techniques that has actually been valuable as well, of course, we've done multiple experimentations and then we've gone into implementation. It's something that you guys might have heard of. It's called isolation forest. I'm sure anybody who's out here who's done unsupervised might have heard of isolation forest. So I've seen a lot of promise that has come out of that as well. I think Gustavo, do all fraud detection methods have to do only with software development or hardware requirements in order to accelerate the system? Absolutely. I think any amount of hardware acceleration would be super helpful, but unfortunately, I do not have the knowledge in hardware. So I'm really sorry. I don't think I'll be able to answer. Once the model is trained, isn't it just like in any other rule? So why is the timing even relevant in this case? So Yusuf, the way rule-based systems actually run their model is very different than how general like CPU-based like ML-based models actually use. One of the things that you do have is rule-based systems that necessarily tend to be fixed. You can't do much changes in it. But ML, you can have a lot of changes to it, and you can have many different features. Like you could have, like, let's say, depth of like 3, and you could have like 150 features out there in a model if you want. But that doesn't solve the problem. So, which is one of the reasons why speed is still an important thing. Fraud detection needs, I think, Gustavo, fraud detection needs to be processed on the edge, or there's a place for cloud computing. That's actually a really great question. If you can process this on the edge, that essentially means that you have really built a great set of features that do not need to connect back to some kind of a mothership. And this goes to historical features. This goes to like longitudinal features, any kind of referential features that you actually want, which essentially means that zero prior knowledge is all the kind of feature sets that you're working on. Because we are not yet there, I would believe that a complete edge-based fraud detection is not yet possible. It's something that I would see from what I can see the space. But if I would be really happy if that comes about. Is there any example you can share for the use case as model identified incidents? For example, model identified important variables, similarities.
So Ashrith,
yeah. Sorry, Bruna,
if you can read it slowly, so the people who are
yeah, of course,
joining, so they know what's the question.
Sorry, yeah.
Go ahead.
I was just in the interest of time, I was trying to read it earlier. Yeah, I think Young's question is if you can share some, is there any example you can share from the use case as the model identified the incidents as fraud? Example, model identified important variables or similarities or other substantiated cases. Young, I think if you can probably reach out to us, we can like give you information about other talks that we have where we've spoken much more in detail about models and the kind of features that we have actually built, if that's any help. I think Almer is the next. James made a question on, Antonius made a question on the public chat that it's very relevant. How is imbalanced data set managed? I think, yeah.
Yeah, sorry, everyone. It's just because we're getting all the questions in the Q&A tab. So it's a little bit hard to follow both, but we'll try our best.
Yeah. I think there's a follow-up question from an,
so there's a question in the chat, and he's asking, how is imbalanced data managed? If you have already mentioned this topic, yeah, I think you mentioned that, right?
Yeah, we just spoke about it,
yeah.
So I think, how do we deal with concept drift? And just retrain daily. Okay, so the drift is an interesting thing. You can retrain at whatever rate that you feel like. There is no limitation. But one of the things that we try to suggest is see if your models are predicting see if there is a significant reduction in your prediction of fraud. If there is, retrain it, or see if there is a significant variation in the distribution of your behavior. Like, let's say your transaction suddenly changed. Your peaks are no more, in the essential transaction value. It's like, let's say, super high transaction value. Then you need to retrain. So that would be something useful if you want to look at drift.
Okay, everyone. So our time is almost over. Yeah. I would like to thank you, Ashrith, and thank everyone who joined. If your question wasn't answered, we've got a lot of questions. We will reach out to you. We will get back to you. And if you have any questions, you can also send an email to Ashrith or to myself. I can add my email here in the chat. So you can reach out to me. And thank you.
Thanks, guys.
It was great.
Thanks for your time. We appreciate it. Thanks.
Bye.